Okay. The recording started. So before you start, Guilherme, I just want to give a brief introduction to this event. So this is a paper club that we do every week. The paper is chosen by every week by a different team member of the AI team here at CloudWalk, and the person who chooses the paper is the person that presents every Friday. Uh, Anything else that I might add to explain what is this event? Okay, no, then perfect. Guilherme, feel free to start.
Okay, good afternoon, everyone. Let me share the window here. Okay, can you guys see it?
Yep.
All right, so the paper I chose for this week is called Growing Neural Cellular Automata, a differentiable model of morphogenesis. And the authors basically, they try to model this process of morphogenesis using cellular automaton and neural networks. Um, so just to give you guys an introduction, morphogenesis is the process of an organism's shape development. So the process of differentiation that the cells go through from a single cell all over to the organism final shape. And the big thing here, which is interesting and hard, is that the cells, they need to communicate with their neighbors in order to grow together um, in the correct way. So part of this part of the secret is the genome of the cells, right? Which is the um, like yeah, they it encodes all the things that they have to do, but they need to kind of do this collaborative process um, in order to know like when to start a specific process, how long it should take, when to stop, and so on and so forth. So they are always connecting, communicating with each other, and this is done in nature by um, receiving like uh, chemical differences and physical stimulus and so on. So a cellular automaton, I guess some of you guys already know, but it's this sort of mathematical model, which is a system made of cells. It's a grid of these cells. Each cell has a state, and each cell has a neighborhood that is defined by the adjacent cells. And the system, it evolves over time. This evolution is determined by a transition rule that is defined for that specific automaton. And at each time step, the cells, they update their statuses, their state, in response to this rule that is previously defined, and the states of its own state and the state of the neighboring cells. So, well, uh, uh, the biggest, the most popular example of this is the Conway's Game of Life. There was a visualization here, but I think it's gone for some reason. But anyways, it's a specific cellular automaton um, that like the cells that are, if the cell has at least three alive cells next to it, then it becomes alive in the next step. And if it has two, it is just stays alive, it's alive. If it's dead, then it stays dead. And if it has less than two alive cells next to it and it's alive, then it dies. So it's an example of an automaton. But the model that this paper specifically they've used is an automaton, so it's a 2D grid. And each cell, instead of being defined by a state characterized by only a discrete value, an integer, they've used a 16-dimensional vector. And these vectors, the the first three channels are RGB channels, so they define the color of the cell. And there is an alpha channel that defines if the cell is alive or if the cell is dead. And the other channels are reading channels, so they are just there for the neural network to decide what to do with it. So it doesn't have any uh, predefined meaning. So since the visualizations were cut from the doc, so just go to the paper itself so you guys can see. But so this is the model. Um, uh, so yeah, I guess it makes sense to show you guys this first. But the idea is there is a single cell, it's a seed cell, and it iterates over time and it develops into the target pattern. So we have all these patterns here. You can choose whatever you want and you start the process. And uh, yeah, the cells they grow together until they become the target behavior. And just show you guys some of the different patterns. But yeah, so uh, this is the model. Each cell here, we have a neighborhood grid, so it's a 3 by 3 matrix. The cell in the middle is the anchor, and each cell has a 16-dimensional channel, as I said. Uh, First, we have the RGB, and then the alpha, which defines if the cell is alive, dead, and so on. And we have the reading layers afterwards. And so at each, this is the neural network. At each step, what is being learned here is the update rule. And the this update rule it's learned based on the cell identity, so the own vector of the cell, and two other vectors that come from this SOBO operator, which is an operation that is used mainly in image processing. And it's a convolution operation. We get these two filters here, and we do a convolution with the states of the cells in the vectors. And this gives us this vector here, these vectors here that encode the gradient, um, the image gradient in that direction. So this first vector here in the x direction, the second one in the y direction. So we can concatenate these three vectors and we get what is called the perception vector. This perception vector is kind of what the cell, that specific cell, this middle cell here, is able to perceive, and it defines how it's going to behave in the next step. So the perception vector goes through this neural network here. It's a very simple, it's made out of a dense layer, a ReLU, and a final dense layer, which outputs this vector here. And this vector is what is the update rule. So with this vector, we do an operation with the cell's original vector, and the result defines how the cell is going to behave in the next step. So the neural network is just to learn this update rule here. And yeah, we have a stochastic update, which is just that the cells, they are not updated simultaneously. There's not a global clock. And this is done just better model, to better represent a biological model, because in a biological system, you don't have this global clock. And this alive masking here is just that um, the cells that are dead, they are their values, their state values, they are set to 0 or 1, I don't remember, but just for the model not to consider them in any way during this process. And and yeah, this is the basically a step, and they perform this step many times. So let me get back to the docs here. Mm. Yeah, so the cool thing about using continuous values for the vectors instead of just a, integer to characterize the state of the cell is that it allows for the update rule to be a differentiable function. And because of that, we can use a loss function and gradient-based numerical optimization, and so a deep neural network. And this way we can actually, the update rule is not preset, it evolves over time. So the cell state, each cell state is represented using a vector of 16 real values, as I said. The first four channels are the RGBA. The alpha channel is used to define if the cell is a mature cell, a growing cell, and a dead or empty cell, um, which is a cell with no mature cells in its neighborhood. And these states, they change. They can change at each step. A cell that is dead can become alive. A cell that's alive can become dead, and so on. The read-in channels, as I said, they have no predefined meaning. The update rule decides what to do with them, and they can be as signaling mechanisms. As I said, like different in chemicals, and pressure and electrical differentials and this kind of thing. Uh, so the transition, the update rule is applied to all cells, the same update rule, but the results differ based only on the cells and its neighbor states. So the update rule that we get in that step, it's applied for all the cells, but obviously they all contain different states, so the results for that individual cell would be different. The perception is the perception factor that I showed you guys. So it's this factor here that we got from these operations. And it's a concatenation of the convolution with sub X, convolution with sub Y, and the cell's own states. So it's a 48-dimensional percepted vector for each cell. The update rule, each cell applies a series of operations to the perception vector. These operations are the update rule. The update rule is learned. Every cell runs the same update rule. And initially, the update rule is just nothing. So, well, I guess I can show you guys already this to gets easier to explain. But so this is one of each step here is just the one step here, one step going through the neural network and update rule that we get from it, and it's applied to the model. We do this operation many times, and at the last step, we get the result and we apply a loss function, and we backprop through time to update the parameters. And so the initial do nothing initial behavior here is that it's just that initially the update will do nothing, and so the first time we apply the loss function, uh, will the behavior will just be the initial seed cell, and the parameters will be optimized throughout time, and eventually we'll get a better and better update rules, and the pattern that we get after all these steps will get closer to the target pattern. So stochastic cell update is what I told you guys, that there is no global synchronization. The cells are updated independently. The leaving cell masking, all channels in an empty cell are explicitly set to zero, so they aren't considering any computation. And so hopefully you guys have an idea of how the model is already. Now we can get to the experiments that they performed. The first one is just learning to grow. So from a seed cell all the way to the target behavior, the target pattern, sorry. They train the cellular automaton to achieve a target image after a random number of updates. Initialize the grid with zeros, except a single seed cell in the center, which will have all channels except RGB set to 1. So this is just so we can see the seed cell in the middle of the grid. We iteratively apply the update rule. We sample a random number of CA steps from the 64 and 96 range for each training step. At the last step, we apply the loss function. And the loss can be differentiably optimized with respect to the update rule parameters by backpropping through time. So one thing that happened here in the first experiment is that the models that they learned to achieve the target pattern after the number of steps that they were trained for. But after that, you guys can see that the behavior kind of explodes. They either grow uncontrollably or they degenerate and disappear. So the second experiment was just to try and stabilize the models so they can persist over time. And they did this by basically sampling a bunch of cellular automata, and but like they did a bunch of trainings, but every training, instead of beginning with models with just one seed cell, they started the models with the patterns that they got from the last training batch, if that makes sense. And so they sampled the models here, and each step they use what they got from the last step. And this way the models learn to stabilize that pattern for much longer, way more iterations. Yeah, so this is training step 100, training step 500, 1,000, 4,000. And yeah, you guys can see that they were degenerating much sooner before, and afterwards they learned to become stable for much longer. So yeah, the third experiment, learning to regenerate. Uh, so it's exactly as it sounds. They wanted to teach the models to uh, grow to the target pattern after being damaged. And yeah, you guys can see they damaged the models and they let them grow. But they're not very good at doing it before the experiment. So what they did was, well, they sampled a bunch of cellular automata, they damaged them, and they underwent some training. And by doing that, the system became capable of regenerating these states damaged by randomly placed erasing circles. So they damaged them uh, using this erasing circles you guys can hopefully see here. And yeah, afterwards, the models that were exposed to damage during training are much more robust, being better at regenerating after being damaged. So this is after the training. You guys can see that they are much better than before. And lastly, they did this experiment 4, which is very simple. They just rotated the perceptive field. So when they perform this operation here with the Sobel filters, um, they rotated the axis for this operation. So instead of getting the x and y, they rotated the axis, and uh, yeah, basically the you would expect this to like be a big perturbation to the models, and they would just not be able to deal with that, because when you do this when you rotate the axis, like the pixels that are in a position when you rotate, they kind of overlap with other pixels. So this is not it's not very straightforward. You actually are perturbating the system. And surprisingly, the models were robust enough to maintain their shape even after doing this, which is something that they were surprised by. Uh, yeah, this behavior is impressive since the rotated pixel will overlap with multiple pixels. And the ability to grow the pattern implies the model is robust enough to behave properly outside of the training conditions. Um, so yeah, these are the 4 experiments that they did. And here you can basically choose a pattern, and you choose a model type. The growing is the first experiment, the persistence the second one, regenerating the third one. And if you rotate here, you are doing what they did in experiment 4. So yeah, you can also make these perturbations here. So it's rotated, sorry. So this model is just good enough for growing, but as you guys can see, they degenerate very fast, and the persistent model, it's stable for much, much longer, but they're not very good at regenerating, I guess. This one's better than the growing though. Now the regenerating is able to, yeah, it's way more robust. There are things that they're not able to recover from though. So if you go like, yeah, if you do a lot of damage, then even the regenerating models are not able to recover from. Uh, yeah, so I guess that's basically it. If you guys have any doubts, comments, um, can jump in and compliment whatever you want to.
Pretty neat paper. I really enjoyed. Anyone has any comments here for Guilherme? Ideas, suggestions, or I don't know, suggestions, not maybe not the best term, but
I
comments in general.
I don't have because I spend most part of my time playing with those applets because I literally don't know anything about cellular automata theory and this kind of subject. So I think that to discuss a little bit further, it will be more difficult to me at least. But it's awesome the way and the architecture and awesome.
Yeah, I like this. It's not, I guess it's not directly useful for CloudWalk in any way, but I find it very neat this idea of uh, like a bunch of different entities finding a sort of bigger harmony, you know, and complexity, higher order complexity emerging from that. I think it's very kind of aesthetic, and yeah, the deep learning part, the neural network is, I had no previous uh well, I had an intuition, but I knew very little about it, and even now it's still, there are things that I don't think I quite get the details of, but yeah, I found this very interesting, the idea of the update rule being um, well, updated. It's constantly learning and so on.
Um, Although I want to say something about Game of Life, maybe.
Well, just want to say I like Cellular Automata. So it was really nice to see this. I I also need some guidance here to know what will be the next paper, so I can try to read it because I'm not sure
Oh,
how you are scheduling it.
yeah, we do have a channel called Paper Club. I'm not sure you are in it. I can
Okay,
add you. And then every Monday we define the paper.
nice.
Um, let's see. Uh, Add. So we go alphabetically every Monday. So Guilherme, I don't know who's next. Let's check.
I am. I am the one.
This how okay. And there are some people that join, but they are not really part of it. But yeah, Israel, the next. Maybe we can kick some people out.
Yeah, there is anyone that will be joining us next week. I think that for next week.
No, we choose the paper. Like
Ah,
if
okay.
you are the next.
The
No.
next week is Sabine.
Ah, okay.
What? Okay. Do you wanna go? Maybe click on this link that Allah sent. Game of Life. I was listening to this lecture from Rule 30. Have you ever heard about the Rule 30?
Yeah.
Oh, this is your game of life. Oh,
The one with a real good UX, you know?
yeah.
Put,
How do you run?
you press 1 in your keyboard, and if you put 9, it will grow faster. So 1 to 9 is the speed which you do.
Oh. And you reach stable condition.
I think there are some pre-patterns here. This R pentamino is nice. You just start, you press R to pop a pattern that will grow in really chaotic ways. It's just a small pattern that grows.
How do you reset the grid?
Well, C. Yeah,
See.
that's the
Okay.
pentamino.
Then
Yeah, this pattern is
cool.
interesting. It's really something simple that grows. I mean, the boundary conditions is important here. We must choose what to do when a cell reaches the boundary. And the rule I'm using here is like it's like Pac-Man rule, you know. If you go to the left, you'll be on the right. It's also known as a toroid rule, I think, because it looks like a torus, and you join the left with the right, the up with the down. You can imagine this pattern living in this torus space.
There are videos of people playing around with the game of life, and they're able to do some absolutely crazy stuff, right?
What
Yeah.
Game of Life has a little bit different from Rule 30, correct? Like Rule 30 goes down a little bit. The structure is different. It's not like a. Can you consider like a 2D space? I don't know. It's more 1D, correct?
Well, you can. I think there are some ways to generalize cellular automaton. The first one is the number of states, because Game of Life only has 2 states, dead or alive. But Conway, in fact, he classified all the rules that you can have, like with 3 states, 4 states, and that's when why he's able to put a number in each rule. He has a kind of categorization for them.
Like, is it Wolfram? You know, Wolfram, like all his stuff. I don't know nothing, but
Yeah, he's very into it. He's written
it is
a
everything
huge
based
book
on
about
Conway. He
automatons.
didn't change anything. Wolfram automatas are the same as Conway automatas, cellular automatas.
No, not really, because he played with more rules, you know, simpler rules. So World 30 is a good example. It's way simpler than Game of Life.
Yeah, that was my question originally. Rule 30, I was thinking about the Wolfram stuff. Like, it creates a random pattern in the middle. The central line is a random pattern. It cannot predict what will be the next. That's what I remember, at least. That's all I know.
Yeah, that was this. This is a book. It's a really nice book, a new kind of science. I mean, it doesn't live up to the title. It hasn't bring a revolution to science, but it's nice to see this cellular automaton stuff that he has here.
Didn't he? I'm sorry.
Yeah, some of his employees, one of his employees, even managed to prove like one of these simple rules are Turing universal. So you should be able to compute anything with these simple rules. Game of Life also is Turing universal. Yeah, some people went to hard work to design a small calculator using Game of Life rules, you know, just start with some initial states, and then it will compute the sum of 2 numbers and all that. So these are powerful stuff, this cellular automata.
Pretty neat.
Doesn't Wolfram have kind of a theory of everything that involves solar automata somehow?
Well, his theory of everything is also more implemented as a graph. So what he does there is like you start with a simple graph and you have transition rules similar to these automata rules that we have here. And then you can kind of grow this graph, from this node, you follow the rules and it will grow. And then he performed some kind of, he derived some metrics from these graphs. One of the nice things that he did was like to compute a kind of dimension. What would be the dimension of a graph? So he came up with some definition of a dimension, and she could like find graphs with fractal dimensions, and also compute the volume as if a sphere is expanding, as if the graph was representing a sphere expanding, stuff like that. But then he went to he says he derived the quantum mechanics and relativity, general relativity, special relativity from these rules. It's something interesting, but I don't know if the real value of it, because it's too, how can I say, this derivation
extreme.
It's really out of mainstream, it's something really different. I don't understand it fully. But it's interesting that he is working with that. In this book here, A New Kind of Science, I first learned about this book in my graduation, like I don't know, 15 years ago, something like that. And then some years ago, in this book, he already started talking about this kind of thing. A graph, the graphs he uses are hypergraphs, in fact, when you can have an edge connecting more than 2 nodes. So you can have an edge connecting 3 nodes, 4 nodes, and so on. And he already talked about this stuff in this book. There's a chapter here called The Applications to Physics. There aren't really any true applications, but he talked about this kind of stuff.
Yeah, I read the preface for this book, and in it he already makes like very impressive claims, right? That he's some sort of revolution that he's making.
Yeah, that's one problem with Stephen Wolfram is it's his ego. He's famous for his ego.
Yeah.
He likes to talk about himself a lot, but I think he is onto something here.
Yeah, but he's smart. He's definitely smart. It's not just ego.
It's interesting. One more thing about this project of his from physics. The latest blog post he wrote about it, he came with this concept which he called the ruleat. It's a structure which contains all possible rules and all possible updates from all possible initial states. So everything is there, because he's trying to answer the question, okay, what if we find a rule that reflects our current universe as we understand it? Then would come the question, why this rule and not other rule? Or maybe there are many rules that would give rise to our own universe. So he just went for the whole thing. Okay, so our universe must be from some rule inside this big object. It's kind of cheating, right? But what is interesting is that he says that if he applies what he learned in this entire object, the conclusion that he arrives at is that independent of the rule that you have, you have physical laws similar to quantum mechanics and special relativity and general relativity. So according to him, there is not much space even in a multiverse. There is not much space if you consider the allowable physical rules. That's something that I find interesting, because one big question is this one, right? Why we live in this particular universe with this particular physical laws?
which are very specific and necessary for, well, everything to emerge, right? If they were slightly different, then
Yeah,
things would not be stable enough.
yeah.
Yeah.
And he makes at least one prediction for this kind of for his analysis. For him, he understands quantum mechanics as similar to special relativity, but only in some kind of in a different perspective, a different view in these rules. For him, the when you have like multiple choices, where you can apply the same rule in multiple cells. How would you choose one or another? According to him, you just compute everything, and then this would give this would mean this would give rise into the quantum mechanics. Quantum mechanics, the multiple choices, and you can create connections between nodes. For instance, if two nodes has the same parent in this graph, so they might be connected in a new kind of graph, like a new connected graph. And if you perform like special relativity in this graph, you will come up with the laws of quantum mechanics. That's what he says. I'm not an expert on this stuff, but it's interesting because he then can predict that as we have this limit, the speed of light is a speed limit in our universe. In the same way, he deduces that we must have a limit to the entanglement speed if you consider uh, how quantum particles would interact and all that. They can become entangled, but there are some limit on how fast a system can entangle itself.
The information can travel, you mean?
Yeah, something like that. But I think that's interesting because I've never heard about that before. Some kind of entanglement speed. Maybe it's something that could be testable, you know. But I like him, so I keep reading. I always read his blog and where his physics project is going. I like Stephen Wolfram. And even if all those things uh, it goes nowhere, I think his work in giving more attention to cellular automata and classifying the rules is an important work. But I talked too much already. Sorry.
No, don't worry.
Yeah. Well, one more thing. So this big book, what was the point? A new kind of science. The main Stephen Wolfram arrived at what we call I think it's called something like the principle of computational equivalence. So he solves all this kind of similar behavior in many kinds of different systems, like the chaotic updating rule 30. We also have this kind of behavior when you consider something like Turing machines with some specific rule updates, and also in this graph stuff, also in substitution systems, which are systems when you just have rules to substitute character strings to generate new strings. And his conclusion is that there is some kind of bigger principle behind all of these kind of different systems. And basically, what says that if two things are like similarly chaotic, then they must have some kind of equivalence between them. But yeah, that's it. One more thing to be cautious about if you will try to read this book is to pay attention to initial conditions. There are some stuff that he says, but when he says, for instance, that some kind of rule is like Turing universal, you might need to have an initial condition, a big initial condition, much engineered to achieve your goals. And also, you take complexity from the model, but you put complexity on your input data. So that's something I think, at least for me, it's always caught my attention, that kind of stuff.
You feel like it's kind of cheating.
Yeah, yeah,
Yeah, but I think that's one complaint that people usually have with theories of everything, because they they usually do that, right? They solve the problem in a way, but uh, they add a lot of complexity and answering unanswered things in other places, right?
yeah. Maybe one example is a string theory, right? They demand the existence of superparticles that were never observed in our physical universe.
Yeah.
So yeah, if you add complexity to your model, you might be able to explain anything, but maybe the price is too high and it doesn't. Yeah, well, there we go to like ontological questions about what's the true nature of the universe. You know, is the physical laws that we observe really represents the true nature of the universe, like, or is just a representation from our point of view using our limited resources? So, so if you get a big theory which explain everything, but what about the everything else that is there and we don't find an equivalence in our physical universe? Yeah, maybe that's something that Stephen Wolfman is doing right now. He just got this big object that contains everything possible, computable, and says, okay, our universe is this kind of structure evolving. you can't you can't tell him he's like I don't know, it's like irrefutable.
But I think just just the effort that he's done trying, I think it's already something worthy, you know, because I think most people would be very scared of trying something like that, and just believing enough in your own work to make these claims. And well, I guess that's something should be appreciated at least.
Yeah, I think at least something one some parts of his work I think might become mainstream one day. I don't know. There are some insights there. There are some insights there. I think this possible equivalence between special relativity and quantum mechanics, depending on your point of view, is something that might bear fruit for more mainstream scientists that would be willing to write papers and publish them. You know, who doesn't like to publish, so it's difficult. Yeah.
Okay, guys, any final comments here? I think it was pretty interesting final discussion. Nope. Okay, guys. Guilherme, thank you again. Pretty interesting paper. I think this is it for today. Let me stop recording. How do I stop recording? Oh, no. That's weird. Let me change my stop recording.